Today we are going to discuss spectral series. As we know that when a white light passes through any prism, a very beautiful pattern of light can be obtained on the screen. And this is called spectrum. Spectrum can also be obtained using diffraction grating. Here you can see it is written diffraction grating. This is a device which has glass with several parallel slits here. And the width of this slits is very small, of the order of micrometer. So when light passes through this diffraction grating, you can see here light from bulb is passing through it. You can obtain spectrum. Here you can see. Now, every element like sodium, helium gas, neon gas, hydrogen, every element in its excited state means when you are applying very high electric field or it is highly heated, then it can make a spectrum. When the light falls on diffraction grating, you can see discrete wavelengths. Here, when ray coming from hot hydrogen, excited hydrogen, and it is falling on a diffraction grating, then you find the spectrum of three discrete wavelengths, separate wavelengths. This spectrum is not continuous. You can see they are separated from each other. And this is falling in the visible range. So hydrogen has three wavelengths in visible light. Here 656.3 nanometer, which falls in red wavelength, red range. 486.1 nanometer. This falls in blue-green range. Now 434.1 nanometer, that falls in violet range. You have one or two more spectral lines in hydrogen atom. They are discrete, separated from each other. Similarly, if you take sodium light from a excited sodium volume, it is either highly heated or a high electric field when is applied on sodium gas, high electric field, and the light passes through any diffraction grating, then you can see two discrete spectral lines, two discrete wavelengths. So in this way you can see that every radiation has its spectrum. Now spectral series. You know solid matter and condensed gases. Gases are very thick like in our atmosphere. When radiations come from these things, and radiation comes from every object at each temperature. So radiations are continuously coming from solid matter and from condensed gases. So you can find a spectrum of these radiations, and spectrum of these radiations are continuous, just like spectrum of a white light. Now, this may be resulted due to interactions or vibrations of atom. We know that in any solid, the atoms are very close to each other. In condensed gases also, atoms are very close, and when they vibrate, they interact. Energy may be resulted due to interaction. But when you take a very rarefied gas, very sparse gas. The atoms are far away from each other. And then you find spectral lines from the radiations coming from. The light comes from rarefied gas, a very sparse gas, where the atoms are separated from each other by far. And when you find the spectrum of those highly excited rarefied gas, then you obtain discrete spectral lines. Spectral lines are not continuous. They are separated from each other. And for each element they have their characteristic spectral lines. So you can correlate the design of a spectral line to that of the interior design of the specific atom. You can correlate because hydrogen has different set of spectral lines, sodium has their different set of spectral lines. So these spectral lines, discrete spectral lines, can be correlated to that of interior of an atom. Now, kind of spectrum. You have two kind of spectrum, emission and absorption spectrum. So, emission is spectrum. When radiations from highly excited whether by applying strong electric field or it is due to very high temperature, then the spectral lines are bright spectral lines on dark background. These are called emission spectrum. The spectrum is called emission spectrum. Here you can see in the diagram, you have several spectral series. Now, what is spectral series? You have series of certain discrete wavelengths, one series, two series. In this way, you have series of spectral lines. And here you have one series. I have drawn one series of spectral lines. This is one series. You can say this Bohr series. In the same way, you have different sets of these discrete wavelengths. This is one Bohr series. Similarly, you have Paschen series, bracket series and Fund series, all arranged in this manner. Johann Jacob Bohr was one of the mathematicians, and once he asked his physicist friend that he was getting bored and he wanted some number to play with. Then he was provided these numbers that comes in spectral series, spectral lines. And then he arranged those numbers in this formula to have any wavelength that comes in these spectral lines. Just like when you have been given this series 2, 4, 8 and so on. So you can make a series, a formula in this form, 2 power n, and putting value of n, you can find this series. Here 2, 4 and 8 and so on. In this way he was given those numbers and he arranged those numbers in this formula. Now all the wavelengths, this wavelength, every wavelength can be obtained using this formula by putting the value of m as 3, 4, 5 and up to infinity. So this formula can be further simplified as 1 upon wavelength is equal to r into 1 by 2 square minus 1 by n square. Here n is any number starting from 3, 3, 4, 5 up to infinity. And r is equal to Rydberg constant, and has value 1.097 into 10 to the power 7 per meter. From here you can find unit. Here it is on the left hand side you have unit per meter. So on the right hand side also you should have unit per meter. Here these are numbers. They have no any unit. So this is the Bohr formula, and this is obtained for Bohr series. For Bohr and you have several series when radiations come from any excited element, then you have series of spectrum. So one series of spectrum that falls in visible range, which can be seen from yourself, that is called Bohr series. So this was about emission spectrum. Emission spectrum was forming on a black background with a bright light. Now absorption spectrum. When light coming from highly heated excited element, when radiation coming from highly excited element and is passed through the cold gas of the same element. Then instead of getting bright light, you will be getting dark light on a bright background. Then for the same wavelength, equally placed on the bright background. This is called absorption spectrum. Here you can see you have bright background and dark spectral lines. Now you have so many spectral series. Here you have visible range up to this, then Lyman series, small wavelength you can see. Small wavelength means high frequency. When wavelength is small, frequency is high, and this falls in ultraviolet region. Lyman series of wavelength spectral series. This falls in ultraviolet region, and this your Paschen bracket series. Bracket series I have not made. Here on the right hand side you have one more series bracket. Then you have Fund series. So all these falls in infrared radiations because of its large wavelength you can see. So this is your absorption spectrum because it is having dark spectral lines on bright background. Now description of all the spectral series. So as we saw that in Bohr series we have several discrete lines with their specific wavelengths, and all the wavelengths in Bohr series can be obtained using this formula. Here R is a constant, a Rydberg constant, and n is a number that is greater than 2, any number. It may be 3, 4, and it is up to infinity. In this way of finding wavelength in Bohr series, you can have so many other series like Lyman series. In Lyman series, the format of the formula is same, but instead of writing 2, you will be writing 1 here, and the number will start from 2 and it will go up to infinity. This wavelength falls in, here you can see, in small range, Lyman series. So when wavelength is small, frequency is very high. So Lyman series falls in ultraviolet region. Falls in UV region. Now Bohr, Lyman, or Paschen. Next series is your Paschen series. So first one has your, this starts from 1 square, this is 2 square. Now in Paschen series, this will be 3 square. 1 upon lambda, you can find all the wavelength in that series. Paschen series by this formula only. And this number 2 will be replaced by 3. So it is 1 upon 3 square minus 1 upon n square. Here n starts from 4, 5, it goes up to infinity. So similarly you have Bohr, Lyman, Paschen, and then bracket series. Bracket series and Paschen series, which has large wavelength, these two falls in infrared radiation. So bracket series, you have 1 upon wavelength lambda is equal to R into 1 upon, just replace this 3 by 4. 4 square minus 1 upon n square. Here n is equal to, starting from, after 4 it comes 5. Starting from 5, it is 5, 6, it can be anything up to infinity. And last series is Fund series. And in this, the wavelength is related in this formula by, when you replace this 4 by 5, you will get Fund series. 1 by 5 square minus 1 upon n square, and here n starts from 6, 7, and it may be any number up to infinity. In Rutherford planetary model of an atom, electrons were revolving continuously outside its nucleus, and they were emitting energy continuously. But the spectrum obtained by Rutherford model were discrete wavelengths. And Rutherford could not explain the spectral lines on the basis of his planetary model of atom. This was one drawback of Rutherford model. Now another thing, the radius obtained by his model could not be found because velocity of electron in its circular path could not be obtained. And therefore kinetic energy of different electrons could not be obtained because they were dependent on radius. Potential energy could not also be obtained of all the electrons which were revolving around a nucleus. Now, Bohr model of hydrogen atom. Niels Bohr combined the concepts of classical concepts of Rutherford atomic model and the early concepts of quantum mechanics. And at that time people were knowing that kinetic energy associated with one photon is equal to h nu. Energy associated with one photon actually is equal to h nu, and this is equal to hc upon lambda. Energy is inversely related to lambda. So if you have discrete wavelengths in a spectral series, so should you have discrete energies also. And then Niels Bohr postulated three postulates. The first one is the electron revolves in different stationary orbits with their fixed constant kinetic energies. You can get it from here. If discrete wavelength, so it should have discrete energies also, and this was Bohr's first postulate. Different energy labels, stationary orbits having their discrete energy labels. Now second postulate. And in these different stationary orbits, they have fixed angular momentum. MVR is an integral multiple of h upon 2 pi. So if radius fixed, velocity is also fixed, and therefore why kinetic energy of the revolving electron in any stationary orbit is also fixed. Kinetic energy is half mv square. Unless v is fixed, kinetic energy cannot be fixed. So these were the two postulates, and the first and then third postulate. When an electron makes a transition from one fixed energy state to another fixed energy state, then energy of one photon is either absorbed or is released. So when an electron goes from higher orbit to lower orbit, it gives out one photon. It frees one photon with energy is equal to h nu. And this energy can be seen in the diagram. I have a diffraction grating on which helium light is falling by helium lamp. You can see. And after scattering, a spectrum of discrete wavelength is seen. Here, wavelength of blue color, red color you can see, and some other color is also visible. Though it is not very clear, so below those discrete wavelengths, I have drawn certain lines related to blue color, green color wavelength, red color. So this is the spectrum of discrete wavelengths. Now, if you replace the helium by neon gas, it has more number of electrons. So the spectrum, the discrete wavelengths will be more spectacular. So you can see neon gas, neon bulb, and its spectrum. It is also of discrete wavelengths. Not all wavelengths are present. In Rutherford planetary model of an atom, we could not obtain radius of the circular path of orbit of an electron, as it was given in terms of velocity of electron in that circular path. So every quantity, you can see Z, atomic number was known, charge on electron was known, epsilon naught, absolute permittivity was known, mass of electron was known, but this velocity was unknown. So we could not obtain the radius of the circular path of orbit of electron. And this is why kinetic energy, which is half mv square, when you bring this mv square on the left hand side, you can obtain half mv square. So kinetic energy could also not be obtained. And potential energy, which is K times Q1 Q2 upon R. Here Q1, charge on the nucleus, and nuclear charge is atomic number into E, Ze, into charge on electron, E. So potential energy of electron in its circular path is equal to minus Ze square upon 4 pi epsilon naught R. This also could not be obtained because we were not knowing the radius of the circular orbit of electron. And this is why we could not obtain the total energy of an electron revolving around the nucleus on an circular path. Now, Bohr postulated 3 laws, 3 rules, and the second postulate is MVR, angular momentum of the orbiting electron, is an integral multiple of h upon 2 pi. So when you use this formula, you can obtain the radius in terms of some constant quantity and also total energy in terms of some constant quantity. So here, when you put the value of V from equation 4 into equation 1, here you have equation 1, Ze square upon 4 pi epsilon naught m and V square. Z square by 4 pi epsilon naught m and V square. V square here is n square, h square, and 4 pi square will go in numerator, m square, and then your you are putting the value of V, so it will be m square r square. And here the value of r is obtained in terms of epsilon naught n h Ze pi m, and this is equal to epsilon naught n square h square divided by Ze square pi m. So now for Bohr's radius, when you put value of Z is equal to 1, value of n is equal to 1, Bohr's radius can be obtained. So Bohr's radius A naught is equal to epsilon naught. It has value 8.85 into 10 to the power minus 12. N is 1, h, Planck's constant, h is 6.62 into 10 to the power minus 34 whole square, divided by z is equal to 1, and E square is equal to 1.6 into 10 to power minus 19 whole square, pi is equal to 22 upon 7, and mass of electron is 9.1 into 10 to power minus 31, and this is how you can obtain the Bohr's radius, and that is equal to 5.29 into 10 to the power minus 11 meter. This is your Bohr's radius. Now similarly you can obtain value of energy of a revolving electron in its orbit. So we know that it is equal to minus Ze square upon 8 pi epsilon naught r. So here I have put the value of r, and energy has come equal to minus Ze square e power 4 m divided by 8 epsilon naught square n square h square. So if you put value of Z, mass of electron, absolute permittivity and H, you can obtain, I have put all the values, you can obtain energy of an electron in its any orbit, in its any stationary level. So it has come in joule, which is equal to minus, total energy is negative, minus 2.18 into 10 power minus 18 divided by n square. And its value in electron volt is equal to minus 13.6 divided by n square. Here negative sign shows that the force is of attractive nature. Now this equation of energy can be utilized in Bohr's third postulate, that is E1 minus E2 is equal to h nu. So I have simply subtracted the two values. E1 minus E2 is equal to h nu. So E1, putting value of NH and 1 in this equation and taking rest of the things common in both E1 and E2. Z is common, charge on an electron is common, mass of an electron is common. So I have taken all the common things outside and keeping n1 and n2, square of n1 and n2 inside. So this is your h nu is equal to minus z squared e power 4 m divided by 8 epsilon naught square h into 1 by n1 square minus 1 by n2 square. And so Sc by lambda is equal to the value. And therefore 1 upon lambda, 1 upon wavelength is equal to, I will take Hc on the right hand side of the equation. So this is equal to z square e power 4 m divided by 8 epsilon naught square h square by c into 1 upon n1 square minus 1 upon n2 square. So all these can be taken as one constant r. And here this wavelength is some length. So I have taken modulus of this so that negative sign can be removed from here. So I have taken modulus on the both sides. And this constant is changed because all the terms are constant and it is replaced by r, which is called Rydberg constant. For hydrogen, Z atomic number is 1. So 1 by lambda comes equal to r into 1 upon n square minus n1 square minus 1 upon n2 square. This is same as Johann-Jacob-Balmer equation. Drawbacks of Bohr's postulate. Bohr's atomic theory explains only hydrogenic atoms, means hydrogen atom, singly ionized helium atom, doubly ionized lithium atom. These are hydrogenic atoms. These have all the positive charges in its nucleus equal to Z into E, but it is having only one electron. When you singly ionized helium atom, which otherwise having two electrons, and when you take out one electron, now it is having all the positive charges in its nucleus and it is having only a single electron. Similarly, in the case of doubly ionized lithium atom, it is having only one electron and all its positive charges in its nucleus. Now, Bohr's postulate could not predict about the intensity of radiation, intensity of wavelengths in spectrum. It could predict correctly about frequency wavelength of the spectrum. But what is the cause of different intensities? When you go towards lower wavelength, intensity reduces. And second thing, spectral lines come close. So these two things happen. Lines come close towards smaller wavelengths in spectral series and intensity reduces, and Bohr's model could not predict about these observations. Now last drawback, that it could not tell about why some transitions were more favored.